How are we doing today? What's the Do you know that's America? If you need anything, just tell me.
Did you have a good lunch? Good. Attendance? No. Okay, I will do it. It's okay.
Can we start? Good afternoon, everyone. Today we continue the discussion from last week. Just for a very brief We're talking about concrete columns. We learned how to distinguish short column and slender column. When we came to the capacity of the concrete columns, we had some graphs like this. And for that one, every graph is for a specific column. Okay? And these two axes are the internal moment and the axial force, but normalized. Don't worry about the denominators, they are just normalized to be dimensionless. And for example, we had a column like this, and the dimensions are 30 by 30 centimeter. The material property are almost the same as assumptions that we took before for concrete and steel materials. And we assume that we have the value for the internal forces from structure analysis. So either ETABS or CAN. And we can simply go to calculate this factor, M2 max, which is this one, over BH2. B is this one, H is 30 centimeters minus cover. CK is the compressive strength of the tension strength of the characteristic compressive strengths of the steel. And again here, this is coming from here. This is the axial force. So we have axial force and bending moment. So we also determine the axial force over BHFCK. With these two values, we can go on this graph and we will go to this part. Okay? Because it's coming from M, it's coming from the axial force. When you're coming from here, this point is something like you're somehow on this curve. This curve is 0.1 in terms of this value. Rho means the distribution of reinforcement in your section area. This is this one. So I just came under the graph. I read 0.1 for this parameter. So I just put this parameter is 0.1. Okay. I have FCK and FYK, and I can calculate rho. Okay. I have FCK and YK, and just substitute these two here. I can calculate rho equal to this number, right? So rho is always AS reinforcement over BD, right? The ratio of reinforcement. AS is in square centimeter, square millimeter, whatever your dimension is, and BD, rho is dimensionless, right? This is a square millimeter, this is a square millimeter, for example. So when rho is 0.005 and you have BD, so you can easily calculate AS is equal to 0.005 times BD. So you will get AS equal to 450 square millimeter. You need this reinforcement in your section. You need to put some reinforcements here to comply with this amount of AS, this amount of reinforcement, right? Longitudinal reinforcement. For this purpose, we need to choose what kind of rebar you want to use. If you remember, we usually use rebar number 6 and number 8 for shear design, didn't we? They are very tiny rebars. Number 6 means the diameter of your rebar is 6 millimeter. Okay? The rebar is, the section of rebar is a square, a circle. So the diameter of that circle is 6 millimeter. Usually we use 6 or or 8 for shear reinforcement. And for longitudinal reinforcement, we usually use something like 12, 16. We have, for example, 18, but we didn't mention it here because we prefer to use, for example, we prefer if we have some beams, some columns, some other elements, we prefer, for example, to use number 12 and number 16, not to use number 14. Or, for example, we prefer to use number 16 and number 20 and not to use number 18. If you use number 18, okay, use number 14 and do not use number 16. What do you think? Why?
Repeat the question, then get it very well.
Good afternoon. We usually put one of the numbers in the rebar if you want to choose some rebars to use in our problem. For example, if I have to use number 12, I prefer to use number for other elements, 14, 18, not to use 12, 14, sorry, 12, 16, 20. Like this, 12, 14, 16, 18, 20. I prefer to use this and this, or this and this.
So that it is easier to differentiate for workers because they would see it and this.
Absolutely correct, yes. Because in the project, when they bring these rebars into the site, it's very difficult to differentiate between number 12 and 14 with your eye, intuitively. So it's likely to make mistakes for the workers. You use 14 instead of 12 or 12 instead of 14, right? That's why we prefer to use, not to use all of the different kinds of rebars in sequence. If you use 12, for other elements use 14, not 16, 18. If you are using 16, don't use 18, go for 20, right? For this example, I'm going to use number 12, for example. If I'm going to using the bar number 12, so I was here. I need 450 square millimeter summation of my rebar. So I need to, for example, I can say 450 square millimeter is n rebar times pi 12. 4, right? And I can calculate n and round it up. Okay, I will get 4 rebars number 12, which have 452.4 square millimeter. It's always the case that what you need to comply with some rebars that are a little bit more than you really need in your section, because you need to use some rounded numbers for the final number of rebars, right? So I use 4. For the columns, you need to use at least 4 because you need 1 in each corner at least, right? This is the schematic shape of the column, okay? But if you need more than 4, you can put here, 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 put wherever you like. And this is the shear. Okay, that one is the shear. The longitudinal reinforcement is coming from the flexure and axial force design. When you design your section, you need to comply with the minimum and maximum values that the code enforce you. Always, it's the case for any kind of design. You need to comply with some threshold, minimum and maximum. For the Eurocode, you have the minimum as this one. The minimum is the maximum value of these two values. Okay, and it is the axial force, FYD, you had it, and AC is the area of your section. Okay, so I want to check it. I'm here. I'm writing this formula here. AS min means the minimum reinforcement you need. You should not be less than that. Maximum of 0.1, I'm reading this, multiplied by this one. This is the axial force. It's in the previous slide from structure analysis. And this is FYD, right? In the previous slide without me. So, and this number multiplied by the area, okay? If you calculate these two numbers, you will come up with 180 square millimeter, which means you have already 452 something, okay? So you are above the threshold, that's fine. And the maximum value is this one, which should be less than that, not crossing. So it's again 4% of your area. Or better saying, if you are using the overlap technology of the reinforcement, it should be 2%, right? For 4%, you will get 3,600 square millimeter. If you go for 2%, you will get 1,800 square millimeter. In any case, you are less than that. You are 400 something. You are way far below that maximum value. So I'm fine. My design is okay. It's between the minimum and the maximum, right? Any question? This is why it's just those formulas with minimum maximum. Yeah.
Is this for steel or concrete?
It's for concrete columns, right? See? It's the concrete column. You have some concrete, the steel is inside. You have a steel, but the rebars are made from steel.
For term 2 tabs.
Pardon me?
It's for the course for term 2.
Yeah, it's the next thing I'm telling you. Well, if you remember for your coursework, one part was left for this term, which was about columns, right? It's this one. So I'm going to tell you how we can deal with this in the ETABS, okay? So if you have done your coursework, you saw that you need to take one of the beams, bring it out to see what are the load combinations, and finally, for any kind of element, any kind of design, you will come up with a kind of demand to capacity ratio, isn't it? What is the demand in terms of shear? What is the capacity in terms of shear? In terms of axial load, in terms of bending? So for the beams, you had only the bending moment, right? You have the demand from structure analysis and the capacity from this bending moment. This. You will divide those together, you will come up with a kind of demand to capacity ratio. The demand to capacity ratio is less than 1, everything is okay, but if it's more than 1, you need to think of something bigger. Your section, use another material, use more reinforcement. These are the strategies you can come up with to just decrease your demand to capacity ratio. But in the case of columns, it's a little bit different because in the case of column, it's not only the design for the shear or the design for the bending moment. As I told you last week, it's the design for the concrete columns, it's the design for the combination of bending moment and axial forces. So this combination makes a little bit complication in the process. So I just opened the previous file we were used to working with, and I just open it to be able to do something. If you go to the section property and frame section, for example, add new property, and here. As I told you last week, those graphs I showed you, the interaction between the axial force and bending moments are very difficult to calculate manually. It is possible, but it's very, I cannot go into the procedure. It needs a couple of sessions to do that, but it's very annoying and very complicated if you want to do that by hand. And ETABS has a very fantastic tool to calculate that graph for you for any kind of section you need. Okay, so it has a capability called Section Designer, SD. SD stands for Section Designer. You can use it for different purposes, but one of them is this one for concrete columns. Still for the structure is useful as well. So if I choose Section Designer, it doesn't matter which one of these sections are. You don't need to use any of these. Just press OK, and you can just my Section Designer. If you open Section Designer, this is the capability. It's very useful. If you open it, you will see that there is a space that you can really draw whatever you want, your section, okay? For example, I want to have a concrete section. Okay, I have some tools here. For example, I can draw a circle section, a rectangle section, any shape section. These are very useful for design of shear walls, etc. So the most simplest way is the rectangular section. If you right click on it, you will see the property. It's the default 600 by 600. Okay, so I can live with that, or you can change it. For example, if you want to change it to 400 by 400, just simply click on it and change it. If you change it, you will see like this. I just zoom in like this, and you can, and this, if you right click on it again, you will see that this is the material. You can change the material. I don't have it here, but you have probably my concrete material, so you can put it my concrete material here, right? So this is a rectangular made of my concrete material, right? So I need to add some reinforcements. You can either use, again, I again right click on it, rebar. I can use a rebar here, yes, rebar number, not number, 8 rebars, okay. Like this, 8 rebars, you can change it. If you click on the rebars, you will see bar size is 25. Okay, I use 18. Just decrease it, right? If you want. If you want, you can use some rebars between, just like a drawing, right? Whatever you want, you can add, and then it's here. You can get the graph that I was speaking about. This is the interaction curve surface actually between M2, M3, and P. M2 and M3 are two internal moments, M2 and M3, and P.
This column is for which location? Because we didn't select any column.
It's just section. It's just section. Then you assign this section to some of your columns.
Where did we get the M1 and like the forces and stuff from?
This is resistance. This is capacity. This is not the demand, right? This is the capacity for this concrete and these rebars. Okay. The demand comes from the structural analysis. They will divide it together. This is what you need to do for your coursework for one of the columns. You need to grab one of the columns out and say, okay, you see, from the load combinations, I have P, M2, M3 in this load combination, okay? And this is my capacity because of this. If I divide these two together, I will come up with the demand to capacity ratio like this. and this is what you see in the ETABS. Okay? This is important. The sequence is important when you should understand what the ETABS is doing when you get some results like demand to capacity ratio. So the structural analysis gives you some internal forces. This is the capacity. This kind of reinforcement, this kind of geometry, this kind of concrete, this is the capacity. Depends on what M2, M3, and P you get from your structural analysis. You are standing in one point, probably, hopefully, inside this onion. We called it onion shape last week, do you remember? So if you are inside this onion shapey thingy, you are safe. If you're outside this onion, the demand to capacity ratio is more than 1, right? That's the procedure you need to follow, but obtaining this onion kind of graph between M2, M3, and P is very difficult to do by hand. It is possible, but it's very time consuming. And this is the art of ETABS, that simply calculate this for any arbitrary kind of section you need, right? And this is a kind of a slice of this onion. So it's a kind of a slice. No, sorry, this is moment curvature. This is something else. So this allows you to, if you are in an iteration process, you can use the section designer and see what is your demand to capacity ratio. If it's like 0.2, you have too many reinforcements, so decrease them, eliminate some of them. You don't need them. It's the demand to capacity ratio is 1.2, it's more than 1. So you need to go there, add some more reinforcement, right? But still, there are some limitations for how many really you can add reinforcement, how much the space should be between them. We'll talk about them probably today as well. Because if you put too much reinforcement, probably you will pass the criteria of 2% or 4% of the maximum reinforcement, or even sometimes you don't pass that threshold, but still your reinforcements are so dense that when you pour concrete in place, the concrete cannot go between the reinforcement, fill them in, and we will have some gap air between the reinforcement, which is not the at all, because basically you should fill the section with concrete without any air. So it's very difficult to fill it with concrete if you have too much dense reinforcement in your section, right? So we continue this subject by going through some very simple regulations. If possible, I want to close concrete today. Probably we will. Concrete structures today, and next week we'll go for structures. So we only have one thing to do, which was again one of the topics from coursework number 1, went to the coursework number 2, which is some criteria about serviceability limited state, which is called in abbreviation SLS. Serviceability limited states. Just to make it more simple, you remember the node combinations we worked with along the whole term. We had some combination of different loads, didn't we? So for example, 1.35 multiplied by dead load plus 1.5 multiplied by live load. Do you remember? That's called the load combination for the ultimate design. Ultimate design, the structure is under all the possible loads that can be applied on it. The load is there, the maximum possible load, live load for all the uncertainties, which means 50% more, is coming on the structure. And everything, earthquake happened, the most intensive wind is blowing. So all the possible loads are applied. If you feel warm, you can open some of the windows. I don't know how do you feel there, but here is very warm. Up to you. You can feel free just to open anything. It's very, your structure is at the edge of the point before collapse. It means that the maximum load is applied on your structure. So it's a very kind of rare situation, isn't it? It doesn't happen every day. It's a very kind of rare situation, maybe happens once in a lifetime, in 50 years, in 100 years. So it's a kind of very awkward situation, very rare situation, but still we designed the structure for that kind of situation. However, on the other hand, the serviceability limited state means the day-to-day life of the structure, not that kind of rare situation. It means that today we are under this roof and the structure should work reasonably for our purposes, right? So we don't need to use those kind of amplification factors, 1.35, 1.5, to increase the loads. All those kind of coefficients are 1. You just add every kind of loads that you have, dead plus live plus. Okay? No amplification factor. And the criteria in the code aims at complying with some regulations that ensures you that the structure works well in the day-to-day life of the structure in terms of, for example, vibration. If I walk on this floor, it shouldn't be so vibrant that the people in the lower floor feels I'm walking here, right? Otherwise, they're not comfortable. They see the ceiling is vibrating somehow, so they may scare, or they don't know if the ceiling can carry those loads or not. It should not be visible, right? And also, this is for vibration, for example. Also for cracking. For example, if I see some cracking on the walls, even if they are not structural elements, they're just very thin walls with some very fragile materials. So I will scare if I see there are some cracks. So it should be, but it happens. For example, if I just go, if your concrete beam, for example, if your concrete beam has some significant deformation, which obviously sits on some infills, some very non-structural walls, so it will make some cracks in this wall because it's pushing the wall down, isn't it? So you see some cracks in your non-structural wall, you don't feel very well. Okay, there is some problem. However, there might not be any problem because the beam is carrying the load, that's fine, and that wall is not structural wall, it's just a filling, infill wall, or a kind of very light wall. Not suppose that wall carries any kind of load for me. But if I see some cracks, this is scary, right? So the code needs to show some respect to this fact that in the serviceability limited state, day-to-day life of the structure, everything works well. So there are some regulations in the code just to ensure this kind of performance. In terms of 3 major categories: stress limitations, crack control, and deflection control. And these are the sections related to these three kind of controls. So don't worry about this part. This is not very complex. It is actually very complex, but fortunately, the code provides you with two approaches. The first one is very, very complex. The second one is just using some kind of tables just to pick up some numbers from the table. So for the first one, there is no concern about a stress limitation because we already have designed our structure elements for the ultimate limited state. So stress in the day-to-day life of the structure should be reasonable. So for the stress limitation, we don't have really too much concern at all, actually. But for the crack control, crack is really a very complex phenomenon. Crack, especially you see a crack in concrete buildings, usually in columns, structural walls, or beams. And you know the concrete material is supposed to crack because the tension part will crack very soon before it goes to its ultimate limit state. And you have crack in your concrete always. So the problem is that you need to comply with some regulation to ensure that the crack is acceptable, is small enough. Okay. There are some kind of methods that you go and calculate the crack. Usually you calculate the crack width, how much the, for example, if your structure has a crack, crack is like this. This is called crack width. How much is the crack width? It should be very tiny crack. Otherwise, you will have some serious cracks and propagate to the other parts of the structure. In addition, the crack problem is that principally air can go in, water can go in, right? If water can go in, if water goes in, your rebars will have some corrosion over time. So it won't work as it's supposed to. And also if air goes, okay, we don't have any water, for example, but still air is a problem because air has carbon monoxide and it also is very prone to corrosion. So any kind of air or water or humidity goes in the crack, reaches to the reinforcements, you will be in the situation of corrosion, especially for some structures that are very prone to some sort of carbon monoxide, like bridges, because bridges, the cars, the vehicles just crosses them, and it's a kind of, the bridge deflects and goes back, deflects and goes back. So the cracks open and close, open and close. It's very small, but it happens. So with this opening and closing, you will grab some carbon inside, and it's very hazardous for your rebars inside your bridge main tower, main beams, or any sort of reinforcement you have inside the concrete section, right? So we need to be ensure that the cracks are reasonable. So again, the code provides you with two different approaches. Approach number one is that it's very complex. So if you want to really go for that, you need to go for some formulation related to the crack propagation, etc. We simply prefer to skip it and go for the second method, which is a kind of simplification of the first method, but just going through some tables to pick up some numbers to see if we are complying with those criteria, we are in the safe side for the crack problem. And for that purpose, we need to have some control on the crack in terms of controlling on our rebar diameter and spacing. So you can imagine if you have some rebars very distant from each other, the crack is more probable, right? If you limit your rebar numbers, rebar diameter and spacing, it means that you distribute your rebars more rationally in your section with appropriate spacing between them. It probably will bring you to a point that the crack in your section will be limited to the certain value, because the rebars inside your section helps to close the crack. You know, a concrete section without rebars is prone to 100% crack, but the rebars inside your section makes it more reasonable to avoid any kind of large crack. So again, we have a kind of table here to define our exposure class of our structure. Usually for regular buildings, we are exposure class number 1, which means that we are dry or permanently wet. So concrete inside buildings with low air humidity is in exposure class number 1. So the other exposure classes are for other buildings or structures which are prone to water or kind of very humid regions, like beside sea, for example, right? But usually for regular cases, we are in the exposure class number 1. So based on this exposure class, we have 3 more tables to pick some numbers from them. The first one is this one, top left. If we are in the exposure class number 1, for example, and the reinforced members and pre-stressed members, we don't have any pre-stressed members, without bonded tendons. So we don't have them. We are just reinforced members. So our value is 0.3. It's the width of our crack, the allowable width of the crack, right? 0.3 millimeter. The cracks should not be more than 0.3. Okay? When we get our allowable crack width, we can go to 2 more tables, which are these 2, to see the criteria about the rebar and the spacing. This is about the rebar, and this is about spacing. About the rebar, it says, which one is your crack width? Okay, I'm here, 0.3 millimeter. This column is mine, okay? And for your steel stress, for example, I'm 240, let's say, megapascal for my steel grade. So in this line and this column, I come here. 16 is the maximum bar size I can use. Right? If you want to use more than 16, you need to use better steel, the top of grade steel. If you use this, if you use this is steel, you can use 25 up to 25. And this one gives me some information about the spacing. So again, my crack width is 0.3, and for this case of steel, the maximum spacing is 20 centimeter. So in this case, for example, if I'm in this case, I need to use reinforcement up to 16 millimeter, and the spacing between 2 reinforcements shouldn't exceed 20 centimeter, 200 millimeter. If you comply with these 2 criteria, you're sure that you don't have any crack problem, right? In addition to whatever you had before. For example, if you need to design for the bending moment, you need to design for the shear force. But when you want to put the reinforcement, you want to select your reinforcement, you want to select the spacing between them, you need to be careful about the crack problem. Practically, you can do whatever you need to do, and at the end, just check these criteria. If it influences your result, your case, just go back and just For example, increase or decrease the bar size or increase or decrease the spacing, if it affects you. But if you check it and these criteria, it's okay, it's okay. Just show that your design comply with this kind of criteria. Any question here? For example, in this case shown here, we have the crack width 0.3 millimeter, the maximum bar size, which should be 16 millimeter, and the maximum spacing should be 200 millimeter. You want to have a break, short break? I feel some of you are sleepy a little bit.
Yeah.
Grab some water, fresh air. 10 minutes. Great. So next.
Is the card?
Yeah.
Yeah, well,
You just, I can't see anything on your screen that's glaring.
Literally just need to get the ones that out.
No, you have to check the sheet stress. From 8 tabs the property.
And then the crack of the word.
Great.
Like full classes of geology.
Kind of. Not really, though.
Where's the university's gonna say?
Yeah. No, I've done one day.
Just one.
how much is
I say get.
Just go through it.
You got geology.
What time can you use with the?
I want to see today.
live load is
I'm just gonna finish.
compliant.
I made a.
Enforces you that you need to have a certain number.
I get what you did.
For of yourself.
Suppose
Suppose weight, it's a kind of another. It's a kind of way that might, like, people share.
Okay. When post.
Yeah, I think that's only.
Slash real.
Where?
10 minutes later.
I see it.
Yeah.
You.
I mean, for example, when you design your beam,
Individual part.
you can have two types of beam, 30 by 30.
So have you guys?
How many types?
The three of them. I've done.
The columns. Necessarily, you don't have only one.
My part is.
Because if you are talking about this level,
3, 1, C.
lower level is different. So you can have 3, 2, 5, whatever types of beam, 3 types of column. Depends on your design.
Then there's another one.
Say, okay, I have 2 types of beam, 3 types of
You
column,
see it, so.
or whatever.
The template.
Like, oh my God, like, oh my God, 30 by 30, stuff like
The three of them.
Yes, because it's 2 stories. It can be.
Individual part you can do.
good if you have at least two types.
To yourself, like you, that.
It's rational. And if you need builds into your project, I don't know, but still for two-story building, yes, which can be.
Okay, there's this concept that you taught us in, I think it was second or third lecture, I can't remember the name, but it's basically like this formula, something transient design.
No?
It's just characteristic load, like all that formula. So are we going to be using that in the course?
And hydraulics?
Uh,
So should
only for serviceability limited state, yes.
So not first coursework?
In the first coursework, principally you have used one of them, which is the ultimate limited state. With the regular combination you have 1.5, 1.35.
Yeah.
That's one of those things. So in the coursework number 1, you have used that one. And coursework number 2, for steel structure, you will use the same. But for the serviceability limit state, you will use something similar, but all the coefficients are 1.
At the
Yeah. And for the results, how would I be able to access? Is there like sorry, I'm sorry, it's just because of stimulating circumstances, I had to start reviewing previous questions, but is there like a lecture or something that directly that shows where I can access these results, like the ETAP results? I'll have to compare the manual calculations to.
It's something we discussed several times in like different lectures and also some of the videos
we write.
in the tutorial section. If you go through the first lecture through the previous lecture,
Would all have to try that.
you should be able to do that.
Thank you very much.
What about? So we talk something about that.
Anything.
Did they know that? They know they know. They ask. Let ask them.
You're getting us a book. What do we have missed?
It doesn't work that way.
Yes, it works. So,
How are you?
Sì, perché non forse. Oh, dai. Secondo me è tutto bene. È come se anche tu prendi. Sai capito?
I've lost condition.
Sessions. That's good.
So, we practically covered the crack criteria by a kind of simple restraints on the number on the reinforcement diameter and spacing. So if you put those criteria on the reinforcement diameter and spacing, you will be fine in terms of cracking criteria. And the last criteria is about deflection. As I said before, deflection is important in terms of limiting the vibration in the day-to-day life of the structure, and also limiting the deflection for prohibiting the potential cracks in the infill walls, like any kind of wall it can occur. So this is the problem that the Eurocode has some recommendation for that. So again, you have two options to go for. The more complex it is comparing the calculated deflection with the limit values, means that you go and calculate deflection based on structural analysis ETABS you're doing, or going for a simple approach by limiting the span to depth ratio according to section 742, Eurocode 3. So we go for the simplest approach again, and you need to use this table from National Annex about finding the best or the limits of your span to effective depth for reinforced concrete members without axial compression. So the above one is the formula if you want to go for, but you're more than welcome to use this table instead of the formula. And if you go for the table, for example, for different structural systems, like simply supported beam, one or two-way spanning simply supported slab, and for example, cantilever beam, for example, if you have two columns differently here. Concrete highly stressed, like if you have, for example, 1.5% reinforcement in your section, it's too much rebar. And this is 0.5% rebar. So if it's the right-hand side column is for the cases of lightly reinforced, and the left-hand side, this one is for very intense reinforcement you have in your section. So, for example, if I am in the case of simply supported beam, and this one, I will get 14. What is the 14? The 14 is, this is 14. The L over D. L is the length of your beam, and D, it's the length of your beam, which means the span. The span is the same as the beam. And D is the effective length, effective depth of the beam we are talking about. So, for example, if you have this beam, these two columns, and you can have more things in the lower stories. If you are talking about this, this is L, and if it has a section, this is the effective depth of the section of this beam. Okay. So, for example, just to have an example here, we are continuing this example. Sorry, it was in the previous one. So, no, we are not following that one. Okay, no, we are not following. This is a separate example. The example says in a rectangular concrete beam, 250 millimeter wide, 500 millimeter depth. So I'm talking about a beam like this. This is 250 millimeter, and this is 500 millimeter. Right? Simply supported over a 6 meter span. This is L. The span length is 6 meter. The length of the beam is almost 6 meter as well. axis to axis. However, it's the effective length is a little bit smaller because of the presence of the columns. Longitudinal reinforcement is AS equal to 1,500 square millimeter. Verify the suitability of the beam with respect to deflection criteria according to Eurocode 3. Okay, so what we need is first calculate rho to understand which column we are living in, because we want to see what is the rho. Is it a lightly reinforced or a heavily reinforced? So rho, the reinforcement ratio is always the amount of reinforcement area you have over BD, effective area of your section. So AS is 1,500 square millimeter. This is 250 millimeter by 475 millimeter. Why 475? Yes. I wanted to ask somebody to wake them up. That's fine. So, as you see, apparently rho doesn't have any dimension. Square millimeter, right? Rho is always dimensionless. So it's 1.26%. Percent means the number is really like this. Right? When you multiply it by 100, you will get in terms of percent, right? So if it's 1.26 in terms of percent, we are somehow in the first column, not the second one. We are living in this column. We are closer to 1.5, not 1.5. Okay, so if we are simply supported and highly reinforcement, we get 14 as the limit for L over D. L over D limit is 14, right? Should be less than that, or better to say, it should be less than or equal than 14. So we have L. L is 6,000 millimeter length of the span, right? And we have D, effective depth is 475 millimeter, in our case already, which leads us to L over D equal to 12.63. And the limit is 14, so we are good, right? If we are less than 14, we are good. So the deflection is in the acceptable threshold. But if it's not good, what you should do? When you change the span, span is coming really from architectural point of view. So in practice, it's really hard to decrease span lengths because you need to have a smaller size for your room or kitchen, whatever it is, and you have some problem with your architecture. You can really not change the span lengths. Whatever you can do is to increase the dimension of your beam, especially the height of your beam, right? And that caused some additional problem, obviously, because you cannot increase the height of the beam significantly because it will go down and you will see it. You have a problem with the finishing. Depends on the case, but you should change something to comply with this criteria. Another question. What if I stuck in a project, come to this point, I get 14.5 instead of 14, I'm not good. I cannot change L because of the architecture, he will kill me. I cannot change D because of, again, some other architectural restrictions, because the finishing line is somewhere and I cannot have any kind of beam more than 500 millimeter. What can I do? What else can I do? I cannot change L. I really cannot change D. And I'm stuck with the ratio of 14 point something or 15 even. And I don't know what to do as a designer. You're a designer in a company. You need to solve the problem. Your supervisors comes to you and say, what shall we do? You're a civil engineer, designer, you need to provide a solution.
Decrease the stress. Decrease the stress. Like,
My bending moment design doesn't work in that case. I need this kind of reinforcement because of my bending moment.
deflecting control. That is the only option possible.
That's always the option of some students as well. For example, not in your class, in some other classes, I told them, okay, in your course, I haven't taken a look at your coursework. I hope I don't see that in your coursework. I told you, okay, you will get something from here, you will get something from here, and you need to show that they are the same reasonably. Okay? And this should be, if you differentiate these two, you should get 0, for example, like equilibrium equations. And they did do that. They did get my point, but they knew that I'm sensitive to this point for marking the courseworks. In the report, they say, okay, 100,000 something, the same number. See, they are the same. But when I open the ECAPS file, it says completely a different thing. When I check the manual calculations, the matrices go. Suddenly, a number pops up without any relevance to the previous calculation. They just draw something for me, paint something for me with the matrices, and at the end, some numbers born, you know? And you can see they are very close together.
That's clever.
And the mark is 0, not 10%, 20%. Mark is absolutely 0 in this case, because it's going to be engineer. You are going to be engineer. They are engineers because they are masters. So if they are going to do that, what else I should anticipate from other students? This is not acceptable. This is not plagiarism. It is not getting some other works to show me. This is not plagiarism. Everything doesn't understand it. Nobody understands this, rather than going deeply into your coursework to see what the students really has done. You know? Be careful, be honest. Honesty is the best thing. And try to learn something. This is the important thing. So, if you don't come up with some kind of criteria, cannot satisfy that, you should not be the student, a bad student. You should not do your suggestion to say, I change the criteria to get the demand to capacity ratio less than 1 or this one less than 14. You're not allowed to do that. There are some more wise decisions. If you think that any kind of question I ask in the class you can answer this one.
Cover, we could reduce the cover.
Anything I asked you, last week you were absent, I was relaxed. Anything, nobody answered, this is the class, you know? Again, you came. I'm joking, don't speak. But just to laugh a little bit, the answer for this question is, you don't have to go for this approach. You have the other approach. For example, here, I told you, in the crack control, in the deflection control, we always have something like two approaches. The first, this one was difficult to do. We just passed it, went to the simpler version of the code regulations. And keep in your mind, always when you see some complex method and a simple method in the code for anything, not for this one, for any kind of calculation, the simple method is more conservative than the complex method. It means that if you go for the simple method and you get the ratio should be 14, you get 15. I'm stuck. I cannot change LD, okay? But if you go to the complex one, it's more likely, it's very likely you will get 13.9 and you're okay. Because you are using a more precise method. It's always the case that the code, all the codes, not the Eurocode, all the codes use more safety factors in the more simplified methods, the more safety factors the code implement in the method. So if you're stuck in a situation that you cannot change some parameters to solve the problem, try to use more sophisticated methods. Always the more sophisticated methods in the code give you better insight in the problem, better safety factor, lower safety factors, better situations for the designer, right? So if you go for this, you will have a better, more beautiful world to live with less safety factors. It's always the case, but you need to put some efforts to do that, because that's not a simple method. You need to go to some more criteria. It's not just a simple table. It's just going to calculate your deflections based on some criteria in ETABS and bring them to compare with the limits, with the acceptable thresholds to see if they are good or not, right? So it's a little work needed. So, any questions so far?
No.
Okay. We have a few minutes to talk about coursework and starting the steel structures. Okay. For the second term, as I told you last week, we will have the second part of our coursework, your coursework actually, which is a steel design. You will do exactly the same building with the same parameters you have done already for the first part, but this time for the steel structure. You assume that the slabs are the same, but you assume that beams and columns are made from steel. Okay? And from the next week, we will talk only about the steel until the end of the semester. Okay? So designing for different things. So you can assume that there are many things different from the concrete. So they are totally different type of structure. So the beams and columns need to be designed again for the axial forces, shear forces, and bending moments, but in a different way of the concrete. So the uncertainties in the steel structure is less than concrete. You can imagine. The more advanced material you have, the less uncertainty you have. Steel is way far more predictable than concrete in terms of material. So concrete is, at the beginning, it starts to crack. We have many problems with the cracking, not this kind of crack, the cracking in the design of bending moment. So majority of the section goes out of the game, and you will count on the very small part of the section in compression and also the steel. And the interaction between the steel rebars and the concrete is a problem as well. And you have many sort of issues like this, But in the steel structures, no, you don't have any these kind of problems. Still, you have a different kind of problem we talked about last week, which is buckling. So because steel is somehow made of some kind of plates, and any kind of plate is very prone to buckling. And buckling is a serious problem in steel structures that you see that we will talk about it in a couple of sessions, and we'll talk about different sorts of buckling in steel structures. And it's very interesting to know how we can design steel beams and columns and even girders to be okay for the different sorts of buckling. That's an interesting topic to learn. And what you will do that in your coursework for the second part, you really don't need to wait for the end of the semester, or middle of the semester, like the previous semester, because you need to learn about loading, stuff like that. Now, when we go through the lectures, you can do the different parts of your coursework because your structure is already loaded. You don't need to change the loading, do you? So everything is ready. You need just to change the concrete to steel, right? Change the concrete to steel and to see how the steel material and the steel sections work for columns and beam. Really, we have only columns and beam. We don't have anything else.
What's the material property?
What property?
What would be the material properties for the steel?
We'll talk about it. I'm just going through the whole picture. We will go through details of the steel design. We'll talk about different steel grades, etc. Okay, I'm just giving you some overview of the problem, what we are going to do until the end of the semester. And also, I will figure out a time just to have a mock test, because I think you need one, at least one. I'm not sure if we thought that you need two, we can do two, but because we are approaching the double semester modules like this is a very long module. So we started from the last semester, the Christmas holidays, and again, the second semester. Somehow you may forget that this was a module and this has an exam at the end. So it's good to have some preparation for the final exam, which is in, I don't know, 3 months. So I will figure out some dates to have some practice, which is mock test. It doesn't have any influence on your marks, final mark. It's just a preparation for you to better perform at the final exam. And the questions on the final exam are really what we talk about in the course, different courses. So if you know how to design for different shear forces, bending moments, whatever we talk about, so you should be fine at the final exam. We don't invent something that you have never seen for the final exam, except for you. What else? Okay, let's take a look at Moodle. I have added some extra files on Moodle regarding to the steel design during the holidays. And I want to bring your attention to this part of the Moodle, resources and materials. So you know that these were in this place, but I added these just to have them. I suggest you to download all of these on your computer and in different folders to have them. These are just the Eurocodes and UK National Annex for loading, actions, and design of concrete structure, design of steel structures. I think I write it wrongly. No, it's okay. So far we were Probably I've mentioned EC3 today in some places. It was EC2, I correct myself. So far we were talking about EC2, design of concrete structures, and hereafter we will talk about EC3, design of steel structures. So this is the text of the code. You can go to different sections when we talk about different things and design criteria. And these UK National Annex just provide with some tables and parameters specifically designed for the UK. It's a kind of annex to be added to the Eurocode to be practical in the UK. So these two are also, especially this one, steel sections. I just try to, it's a folder. I just went through, see, it's a folder. If you go through it, I don't know how, if you can download all of them. Yeah, you can download the folder, a single file. So there are some files. These are all about steel sections. So as you know, for example, European English. For example, IPE sections. We'll have some tables like this for steel. You didn't have something similar for concrete. There are some booklets like this. It's PDF. So in the design offices, it's probably usually more convenient to have their booklets beside your hand just to take a look at it. It's easier probably than the PDF, but it has the properties for this kind of section, which is called IPE. It's a kind of I section, isn't it? So these are standard kind of steel sections used all over the world. Made of steel, the shape is kind of standard. So if I just a little bit zoom in, you will see you will have these parameters in your section. D is the width, H is the height, U is from here to here. And these two are called flanges. One top flange, bottom flange. And this is called web. In the I sections, we always have two flanges and one web, usually. And when they are made in, they're manufacturers in some factories, so they are not made on the spot. They are under very controlled situations, very high quality situations. So they are quite different from concrete sections which we make on the side. When the web goes to the flange, it's a kind of a quarter of a circle. It's like a, I cannot write now, but you see R. See, this is the radius of this small circle. It's a quarter of a circle. Maybe I can write here. This is the web, and this is the quarter of the circle, then the web. So a very smooth connection. So this is the R, the radius of that circle. So TW is the thickness of web. TF is thickness of flange. So everything is defined separately for flange and web. And you can see the table here. For example, IPE is 160. This 160 stands for the H. See, this is the 160. This is 160. We call it IPE 160. So the height is 160. And you have B, TW, TF, R, and D. All the parameters defined on the shape. And so the ratios for local buckling. This is something we will talk about next week. We'll see what does it mean. Second, moment of area, the I factor. Remember, we had I in structural mechanics. This is the I factor for the axis YY or ZZ. Doesn't show the. Usually for the British standard, this is the axis and this is Y axis. Okay. So it continues actually. The table is long, it continues here at the second page. You will have radius of gyration as well. The square of I over A, we talked about it last week. You have elastic modulus and plastic modulus. We will talk about them next week for the steel design. You have buckling parameter, torsional constant, warping constant. We will talk about torsional constant, warping constant in a kind of buckling which is called lateral torsional buckling, and area of section. Because you need these tables. You cannot calculate the area of section by hand because it has some small connection of circle, you know. And mass per meter. So these are a profile you can buy and use in your construction site. So a profile is usually provided in 6 meter lengths, usually. So they put them on a vehicle, big vehicle, bring it to the side, but they're usually in 6 meter profile with this section. So with this section, every meter's weight is like this, 15.8 kilogram per meter. So 1 6 meter profile will weigh like 6 times of this 15.8 kilogram. So yeah, that's different. You also have the other files. The other files, it was for IPE. This is the HE section. This is the difference kind of standard. This is HE section. This is the angle section used for some kind of connections, etc. This is kind of W section. These are usually used in the United States. It's very common practice to use W sections. If you, probably not you, but it is I-beam, but it's a standard of W section, wide section. The flange is wide, unlike the IPE. IPE flanges are very, the width is not too long. But wide sections are, this is schematics showing of the section, but section is like a wide flange, You can probably see, yeah, here. For example, H and B are equal to 15. In the IPE section, it was not like that, was it? In the IPE, where is it? In the IPE, see, the H is 16 centimeter, but the flange width is 8 centimeters, almost half. But in the W section, it's not the same, but you can see it's quite bigger than the IPE. It's common practice in the United States to use W sections. If you see some files of the ETABs, if in the manual, etc., you will see that all of them use W sections. This is another section like U section. It's like a U. It's called parallel flange channels. Channel section or a kind of U section. If you connect two of them together, you can make a box. Right? If you connect two of them face to face, you can make a box. However, you can make a box by connecting 4 plates together as well. 2 different ways to make a box section. Box section are good for columns. Usually we use IPE or W sections for beams. W sections good for beams and columns, but IPE sections are only good for beams. They are not good for columns because the flange is very small. But you can make columns with box sections by connecting these 2 channel sections, but all connecting 4 different plates together. Makes a very good section for columns because the second moment of area is somehow strong in the box section rather than the I section. We have also some unequal angles like this. The different legs are not equal, they are different. So you can use for different purposes if you need. We also have universal beam sections. This is another kind. This is common practice also in Europe and UK. Universal beam sections. They are different from IPE and also different from W sections. They are another standard of steel sections. And universal columns, which are somehow similar to W sections because the flange is wider. They are comparable to the W section in the United States here. Universal column section. So usually when we design a kind of element like beam, whatever, when we go to the design procedure, like in the concrete design, we come up with some necessary AS. We need AS equal to 400 something, like today we did, right? In the steel design, you will come up with some A, with some, for example, with some I, which is necessary, the second moment of area. So if you need some threshold for the I, the second moment of area in your design, like you can go to like we say 9,000 something, or 10,000 square, not a square, centimeter powered by 4. This is the second moment of area, this column. And these 2 are second moment area for this section. For example, this is the strong section, this is the weak section. If I need 9,000 something, I need to go here. If it's 9,600, I need to take this, the next one. I need to take this one. This section is good for me. If I go through the procedure and get the necessary second of moment of area is 9,600. So I go to this line and this is my prepared section for the design. So if I check some other criteria, so I can go down. The more down you go into this table, the stronger section you will get. So you don't need to waste money. You just need to find where is suitable for you and optimized for you, okay? Just to find where is the best place to select your section. Also, I put this link here for you just to take a look at europeanapplied.com. It's a good website just to see different properties of different steel sections. It's a useful thing just to take a look, and it's something similar to what I said about different profiles and steel sections, just to see which one has what properties and where they use it. It's a good website just to use along with the Eurocode 3. So you will have the necessary codes here and the steel section properties. If you want to design something, we can just quickly go to those tables and pick up some section for our purpose, bring it and use it. So we don't calculate the second moment of area by hand. We just use those tables. Just go to them and pick the right section, bring it up and use it in our design, right? This is what we will do from the next week. And we will enter to the steel structures world, which is somehow a very beautiful word to learn new things about steel structures. Any question? We practically finished with the concrete, but however, I want to emphasize here when you're transferring from concrete to steel. Design is a long way. It's not like you say, I'm done with the concrete, I'm done with the design. When you start with the design, you just started. No designer can say, I know everything about design. Nobody can say that, can claim that. The design process, civil engineering, specifically the design process, is a lifetime career to learn new things. Believe me or not, when you get more experience in the design for a long time, you will figure out that the design of structure is more art than an engineering science. You will feel something with your structure that you're designing. You will feel about how the different loads are transferring between different elements going through the foundation and there. So never say, I'm done with the design, I'm done with the code. You just started to learn the design. When you go out of the university, probably if you go to some firms to design structures, you just start what you have learned in the university to use there, but still there are too many things to learn during the lifetime of your design procedure. So always there is something new to learn, always, remember. And this is time where really, because of the time limitation, I cannot spend more with the concrete. Otherwise, I can really go through the whole second term just for concrete, but I need to stop it somewhere and transfer to the steel structure design. This is where we go to the steel structure design from the now and from the next week. So bear with me, please, and prepare yourself for upcoming mock test as well. And also, please try in this semester, try to do the coursework during the semester when we go through different stuff for the steel structure. Everything is prepared. And you don't need to change the loading, you just need to switch to the steel structures for the beams and columns, okay? Any question? If not, that's for today and the class is dismissed.
I have a question. The Q&A sessions, are they still taking place? Q&A session?
Yes. Yes, I already sent the link, didn't I?
No.
Yeah, I did. Before Christmas, I sent it.
Until,
I will send it again,
yeah.
but not from this week, probably, I'm not sure, from next week or this week, but you will receive it. So, I will send the link again.
It was not there.
If I need the QR code, please just use it.
No, that-
Yeah.
That's not question, by the way.